just heard a fantastic talk by Andrea Antoni, and she is from Berkeley. And for anyone that may have missed, we will hear another presentation, and she will be first to speak about low time commitment but high impact, informal mentoring of first-generation college students from local community colleges. And Andrea is very inspiring both in terms of her research but also in terms of her outreach work. So we very much look forward to that. And then we'll hear from Emily Pass. Is Emily here? Oh, over there. She's local, of course, and she will talk about the Spindown of Lomas and Dwarfs, insights and challenges from Binaries. And then we'll hear from Christos Panagiotou from MIT. Is Christos here? Yes, over there. Not very far from us, but we don't often see the MIT colleagues. And he will tell us about the luminous, dust-obscured, tidal disruption event candidate in a star-forming galaxy 42 megaparsecs away, pretty close to us. And finally, we'll hear from Matt Holman, our own, and he will talk about assist and Ephemeris-Quality test particle integrator. So it must be abbreviation for something, and we'll learn more about what it means, assist. But we'll start with Andrea. Go ahead.
Okay, thank you. Hello, everyone. Thank you for coming. It just now occurred to me at this very second that the colloquium I gave was talking about unexpected outcomes following failed supernovae that actually do explode. And so the other thing that is very interesting is sometimes the paths of first-generation college students can be very different from what many of y'all kind of followed. And so the outcomes can be maybe quite unexpected compared to what maybe some of the false conclusions that people make about these students. And so I just want to kind of talk about what first-generation college students are, and also talk about this program Power at Berkeley, which is this graduate student run program that's a mentoring program and workshop series. And I actually, by complete extreme coincidence, two of my fellow Power Workshop coordinators, Eliza Beveridge from Berkeley, is visiting Charlie Conroy this week, so she's here. And then also Hannah Kanegi, she and I have been doing the workshops for Power since deep in the pandemic together. We actually didn't meet in person until like a year and a half into our friendship. And she is also here. And so now she's a postdoc doing very important work in atmospheric chemistry at MIT. And so she came to join us today. Okay, and then of course we have a bunch of other graduate students, and we're from all the physical sciences at UC Berkeley. And so I'll just start with kind of my general motivation is that, as Avi and I were just talking about, that I'm a first-generation re-entry community college transfer student. There's a lot there. And I mean, really, the truth is that I am here as a direct result of the mentoring I received and activities that I participated in that are similar to the things that we do with Power. Okay, and so just what's a community college? You have them here in Massachusetts. So actually, Massachusetts has a very similar system to California, where you have these two-year degree granting institutions where students get associate's degrees. You also have the teaching-focused equivalent of the California State University system. So these are the CSUs. And those give four-year degrees. Some give master's degrees in some fields. And then you have the UCs, like where I am at UC Berkeley. So these are the sort of R1 research-focused institutions granting PhDs and four-year degrees. Okay, and so in Massachusetts, you actually have the three kind of equivalent things. And similarly, students can go to these two-year colleges at any time and without time restraints, can work full-time and actually complete their transfer requirements to these other four-year institutions at the community colleges. And so there's actually transfer agreements between, let's say, the community colleges, Massachusetts, and these other types of institutions. Okay, and so for me in particular, I started at, oh, my thing isn't showing up, so sad. Oh, yes, so I started at West Valley Community College, and then I transferred to UC Santa Cruz, where I studied astrophysics with Enrico Ramirez-Ruiz, and now I'm at UC Berkeley with Elliot Quaddard. Okay, basics. So a first-generation college student, just sort of the general definition is that the student does not have a college-educated parent or caregiver. What's really important to realize is that something like half of first-generation college students are also low income. And this is very low income. This is like $24,000 a year or less in household income, or $34,000 depending on the year that you look. And so first-generation and low-income students is this group of students that also tend to be sort of minoritized or oppressed along many axes besides just income. And so these first-gen low-income students are more likely to be female, come from a minoritized racial group, be independent, meaning that they don't receive support from their parents, have dependent children or be single parents, that was me, and work full-time while they're enrolled in college. Okay, and so some of the outcomes as a result of these axes along which school is just harder for these folks, is that they are half as likely to complete a bachelor's degree. This is over a long time integral of 6 years. And they're 4 times more likely to drop out after their first year of college compared to students who don't fall into these two categories. And what I really, really want to emphasize is, because I hear this a lot in academia, is people cite a lack of preparedness for these students as a reason why they drop out. And I can tell you from the research that is an extremely minor reason why these students drop out. The overwhelming reason that students drop out is for financial reasons alone. Okay, and so one of the things that we can do, apologies, my transitions are not working. I don't know what's happening, sorry. Okay, so we're going to skip the last quote. So the quote that didn't show is basically that first-gen low-income students who reported having even one mentor when they were in community college were dramatically more likely to persist past that critical first 2 years and actually persist to a bachelor's degree. And so there's 2 quotes. I read these actually when I was still an undergrad. I've updated them to more recent research, but these really had a big impact on the way that I think about this. Is that, and I'll just read, so being part of a trusting mentoring relationship is especially crucial for women, underrepresented minorities, and first-generation college students in the physical sciences. This is from a study of the Sundial Project at Arizona State University that I think is in physics, which is a peer mentoring program. So they benefit more, but they're less likely to actually be able to develop those relationships. So first-gen students are significantly less likely than continuing generation students to report having a single mentor while in college. So, and I think this is true along different axes of minoritization in our field, is that the students who have exponential benefit from these resources are the least likely to go out and create those relationships on their own. And so therefore it's up to us to intervene and make sure we're engaging these students and giving them really crucial information that they need, and the time commitment for this kind of work can actually be pretty small. Okay, and so basically, if we can just lower barriers to persistence in science by making it easier for students to connect with mentors. And so this is one of the motivations for POWER, this program at UC Berkeley that I told you about. And so just briefly, so POWER is a mentoring program and workshop series for community college students interested in the physical and biological sciences. We primarily serve students from minoritized genders, but accept kind of anyone who applies. And we are aware and cognizant that over the last 20 or 30 years, most affirmative action and DEI work has primarily benefited white women. And so we don't want to do that. And so what we do is, we are at a public institution, and in California, affirmative action is illegal. So the way we get around it is we specifically advertise to and recruit students from community colleges with high percentage of Black, Latinx, Indigenous, and low-income students. And so that's how we try to make sure that we're, focusing these resources to the students who have, many axes that are limiting their access to these programs. Okay, and so everyone's names was on the slide, the first slide, but basically we have a whole team that does workshops. That's the 3 of us are here, and Megan. We have 3 grad students who do all the finance and logistics. There's no faculty involved. There's no external money, so every semester we have to go out and find money. And then we have 2 people who do mentee engagement and engaging with the local community colleges, and then 3 people who do mentor training and recruitment. And mentor training is a big one. This basically does not exist. And so Emma And another student who was in chemistry that's now graduated basically developed our entire mentoring training program. Okay, I think I'm running out of time, but I don't think I have much. Okay, and so the overall aim of Power is really to, this is important, address both sides of sort of DEI work, and that is both to address access to science fields, but then also making sure students can gain a sense of belonging in those fields once they're in those environments. And so there's a few activities that we do to kind of do these things, we hope, which is each student gets paired with a UC Berkeley graduate student mentor across the physical and biological sciences. And the students meet virtually just 3 times per semester with these mentors. So the time commitment on the part of the mentors is actually very small, but the information that these students are able to have access to is really priceless, and I'm saying that from personal experience. And then the other thing that Eliza, Hannah, and I and Megan do is we put together workshops, Q&A panels to demystify the transfer process. We have someone from financial aid come and do presentations for the students, and we try to also demystify pathways to a career in science. Now, the really big reason why we started Power, now this was during the pandemic, so everything was virtual, but finally this year, we were able to have our much dreamed of on-campus all-day retreat for the students. So this was last month, and we spent a whole Saturday with the students on the UC Berkeley campus. And so this is who was left at the end of the day. I want to emphasize that about 1/3 of our participants had to leave early and missed the financial aid presentation, ironically because they had to go to work and had to take the BART to other parts of the Bay because they don't have access to a car. So this was one of our speakers, sorry. So we had icebreakers, lab tours, and what I want to leave you with, so I don't have time to talk about the support network framework, I want to leave up, these are things you know that likely you take for granted that a first-generation college student has no access to because nobody in their lives, this was me included, has access to this information. One of the simple things, if I can take 30 more seconds, is I was just talking to a CSU professor, because I'm interested in teaching in a CSU, and he told me a story about my advisor. 20 years ago, they had a 15-minute meeting. He was an international student. He wanted to get a PhD. He thought he had to go to Europe because he couldn't afford to go to grad school. He goes to my advisor, Elliot, says, my parents don't have any money. I think I have to go to Europe. I really want to do astronomy. I don't really know what to do. And Elliot is like, wait, what? Physics and astronomy programs in the United States are mostly funded. You don't pay for them, they pay you. And so 20 years later, this person meets me, and this is the first story that he tells me. And so you can just take this list, and I'm sorry that I went over time, and thank you so much.
You're doing such an important and inspiring work. Thank you so much for doing that and inspiring us. From your perspective, is it, in terms of the mentoring, is it the fact that those students are simply not aware of opportunities?
Yes.
Or is it more to do with the skill set that the mentoring provides?
No.
Yeah.
All of us are totally unprepared to mentor these students. I mean, unless we're regularly, confronting our own biases, confronting our own racism, really thinking about the complex myriad of challenges that these intersectional students face. Each and every one of us, I didn't have time to talk about this mentoring myth. In the movies, there's Gandalf and there's the Karate Kid. There's always this mostly old, usually white guy who knows everything about every part of our life, and they can counsel us on everything. That doesn't happen, right? Each of us is the integrated history of ourselves, our family, our culture, our values. The racism that has been directed at us, the sexism that has been directed at us, the anti-trans legislation that's in the news, right? And so the only perfect mentor for us is ourselves 20 years from now, and that can't happen. So instead, what we all do is we form this support network, and this is the foundation of Power, is that we work with the students, and honestly, this inspiration comes from a workshop for junior faculty and senior faculty. At every career stage, you have to say, what are my goals? What are the buckets that I need help? And identify resources to help them, right? And so one of these things is awareness of opportunities, as you said. And the reason I am an astrophysicist is because I was applying for a transfer guarantee to UC Santa Cruz, and I checked this box that said TPP. I had no idea what it was. apparently there was a transfer preparation program. So they invited me to a STEM transfer day, and I knew I liked coding and math, and there was this flyer for computational astrophysics RU. I don't know what the heck that is. But my girlfriend, who I convinced to come with me because we were both so nervous about being at a university campus, was like, let's apply, we won't get it, but we'll just it's fine. Well, that actually started me in astrophysics. I actually wanted to be an electrical engineer. I was planning to transfer and do electrical engineering. I wanted to, in equipment, you actually have to model all the sound and heat interference from all the components to get very efficient, internet processing. That's what I wanted to do. But lo and behold, there's this flyer, and my friend convinced me to apply, and I get connected with Enrico Ramirez-Ruiz and Morgan McLeod, and my first lecture on stars, which was taught by Anna Rosen, who used to be here, I found out when I met her, she was a PhD student. She had been a transfer student to UC Santa Cruz. It never, ever, ever, ever occurred to me that I could have a career in physics or astronomy, or that I could get a PhD until I met Anna. So that was and so she gave me my first lecture on stars, and I was hooked. And so that was 2 hours of her time, totally changed my life. Enrico's Lamont flyer totally changed my life. So
it sounds like part of the issue, the problem is communication, somehow letting people be aware of the opportunities.
Yes.
Which may not need mentoring directly, but
well,
somehow communicating.
And I'm not talking about mentoring. I'm talking about being part of somebody's support network. Right.
Questions?
Yes.
Yeah. Go.
So I'm looking at this. Yeah, for those of you who don't know, I'm originally from Russia. I'm sorry
Yes.
for this. So, don't you think that you're actually addressing the basically the symptoms, not the root of the problem? The root of the problem is that you have to pay for the education, which is unaffordable for poor people, while in Russia or in Europe, education is free for everyone. So if you want to engage in university, you don't have to look
I totally agree that the capitalist structure, poverty in the United States since the history of our country, history of enslaved folks and poverty is a huge problem. But the simple fact of the matter is that today, tons and tons and tons, almost all of the first generation students are going to community colleges where the faculty maybe have master's degrees, and they're great. My physics teacher, amazing. He's definitely going to come to Berkeley to come to my PhD hooding or whatever the thing is called, I forget. But no, I absolutely agree with you, right? But here's the thing though, is that if we take students from these oppressed groups and they become grad students and they become postdocs and they become faculty, right? Then those students see these role models. There's other people that they can talk to and actually get access to this information. And my favorite quote from my advisor, Enrico, is that mentoring can change the entire history of a family. And sometimes he does things funny in translation, but what he means is, and this was an article about me and some of his other students, is that, I come from a family, this is a little bit TMI, my dad is a homeless drug addict. My parents never went to college. My parents were never home at the same time because they couldn't afford a babysitter. I meet Enrico. I have Morgan as a mentor. And this now will change the entire history of my own life and the forward history of my family. And so, yes, it's a Band-Aid. We want to solve all those things, but they're never ever going to get solved. We're going to kill the planet first, which is another problem. Sorry.
Any other comments? Yes, go ahead.
So the answer might be okay, but I'm curious about the mentor training for
Yes.
I see with other grad students. Is the main focus kind of teaching them this sort of model, or what do you focus on when you do that?
All anti-racism. Yeah. And it's not great. It's actually really bad mentor training. But several of us tried for months and months and months, 2 years, to try to get the whole physical science and math division to actually pay somebody to come in and help us with this training. And so what we do is, also kind of inspired by this Sundial project that I told you about, is we give reading, we give videos to the mentors, they answer a questionnaire, and then Emma and her team, what they do is every month when they're supposed to have the meetings with the students, we give them discussion points. And our in-person event, we definitely invite the mentors, because honestly, they need to learn more about this stuff than the students do, because the students are living it. And so, all mentor training, if it's not addressing the idea, the power dynamic of mentorship, I didn't have time to show you the slide, but it's really the student-centered thing. It's not some wise person giving information down. The student drives the thing, and all of us as mentors, as colleagues, as attendants, as talks, need to be challenging our own systematic biases. And so what we do is we just kind of make sure, like, hey, in case you don't know it's 2023, like, remember these videos, remember these articles, write us something about it. And no, it's not perfect. And so this is something where it needs to be more, I think, top down, where somebody with $100,000 can hire, let's say, Nicole Cabrera Salazar. I'm name dropping because I'm hoping one of you do this, is hire her to actually come in and put together a mentor training program for astronomers. And it is something that she does individually that you can sign up for. And in fact, the AAS had just sponsored, like 20 people could go attend her training for free. But we do need better mentor training. But it's sort of reading materials, and the focus is on sort of anti-racism. Yeah.
Andrea, you're
Yes.
such a treasure.
Okay. Sorry.
No, one request. Please
Yes.
keep doing what you're doing.
Well, and also like Eliza and Hannah, and I mean, there's like 13 of us, and we meet all the time, and we challenge each other. Like, no one is in charge, and so if you've ever been on a committee of 13 people, like, we're getting some real skills that we're going to use as faculty. But really,
That's
it's.
exactly my point. You should all become faculty and change the world. That's it.
But all of you have the power, and that's the point I want to make. Yeah.
We'll help you as much as we can, but you can change the world. So, thank you.
Okay. Thanks, everyone. You can all still hear me because I'm still wearing the microphone. I'm glad I didn't say, I can't even think of an example of a bad thing to say that you overheard. Sorry. I'm just not evil. Oh, that thing is annoying. Here's that.
That's bending. I hope it's
I'm
turning
gonna
off.
hinge.
There.
It seems to be working well. I'll hold this until you do the pocket thing.
I haven't used one of these before. I don't
I know. Just put it on your sweater. Yeah.
Thank you. Great. Hi, everyone. So I'm Emily Pass. I'm a fourth-year graduate student here working with Dave Charbonneau. Today I'm going to be talking about the spin-down of low-mass M-dwarfs, and in particular, what we can learn using binaries and also the ways binaries can get in the way of understanding what's going on. So many of you are likely familiar with the idea of gyrochronology. So it's using stellar rotation to infer stellar age. So it's a technique that's used for sun-like stars. The idea is that you can look at stars in clusters where we know the age, and you can probe how rotation rate is changing over time. So for these sun-like stars, it's been shown to follow what's called the Schumann law, which is the equation here. So the rotation rate is proportional to age to the negative half. And so this means that when we observe the rotation period of a star in the field, we can estimate its age using these gyrochronological relations. And this is fabulous for sun-like stars, but unfortunately it does not work for M-dwarfs. So M-dwarfs, especially the low-mass, fully convective M-dwarfs that I'm going to talk about today, are very different, especially in their rotation behavior. So the fully convective ones are the ones on the right-hand side of the plot, and are what I'm going to focus on. And so with these fully convective M-dwarfs, what you see in the field, like this population observed by Mirth, by Elizabeth Newton in her thesis, is that there's two different modes. There's two different populations of M-dwarfs. There's this rapidly rotating population and a much more slowly rotating population. And importantly, there's this big gap in the middle. And this, even though we don't know the ages of these stars in the field, it's telling us something very important about how these stars are spinning down. And specifically that they're not following a Schumann-like law. Because if they were gradually spinning down, you wouldn't see this bimodal behavior. You would see lots of stars in this gap. It would all be completely filled in. So the distribution of M-dwarf rotation periods in the field is telling us that there's an abrupt transition in the rotation rates. And based on galactic kinematics, studying the age of the lower population and the age of the upper population, it's thought that this transition happens probably around 2 to 3 billion years on average, which is very interesting, of course, but also what we want to do is get age estimates for specific stars and begin to understand whether or not all these low-mass M dwarfs are making this transition at a similar age, or if there's a big dispersion in this epoch of Spindown. And this is an important distinction if we're interested in the planets of these stars, like I am, because if all of these low-mass M dwarfs remain active and rapidly rotating for billions of years, that's not going to bode the best for the atmospheres of these planets that are orbiting them. But if some are spinning down earlier and some are spinning down later, you could have a much more of a diverse population of planets and their ability to retain atmospheres. So we want to understand when these low-mass M dwarfs are spinning down. And I mentioned that for sun-like stars, we can use gyro chronology, we can use these clusters. And so you might think we could use similar cluster strategies in order to study these low-mass M dwarfs, but it is very challenging to do so. And that's because all of the clusters where low-mass M dwarfs have had their rotation periods measured are fairly nearby. And so the oldest ones where we have good measurements are Praesepe and the Hyades, which are only around 600 to 800 million years old. And so if I put this fully convective line on again, and the axes are flipped now, so we're talking about the left-hand side being those fully convective low-mass M dwarfs, what you see is that while early M dwarfs, you can see my cursor, right? Yeah, early M dwarfs have converged to this slowly rotating sequence by 600 million years. All the fully convective M dwarfs are still very rapidly rotating. So if we want to probe their spin-down behavior, we need to go older. But those older clusters are too far away for us to observe the rotation periods of these very faint M dwarfs. So we need some way of studying the rotation periods of stars, of low-mass M dwarfs with known ages, but we only have access to more nearby ones, so stuff in the field where we don't know the age. And so a way to get around this is by using binaries. So these wide binaries are systems where we have our low-mass M dwarf that's hard to age, and its widely separated companion is a sun-like star or a white dwarf, and we do have techniques of aging those stars, like gyro chronology or white dwarf cooling curves. So this is that MERF sample I showed before, all the M dwarfs in the field, and also those are the stars in Praesepe, those 600 million year old stars. And now I'm going to show you a sample that we collected of M dwarfs with aged, widely separated companions. These are results that are from our paper last year. So these are the collection of stars that we observed, with the color indicating the age of the M dwarf. And even though it's a small number of stars here, you can already see some very interesting things about how these M dwarfs are spinning down. So first of all, if you look at the very young stars, the ones that are less than 1 billion years old, you see a very large dispersion in the rotation periods. Especially there's this one up here that's already made its way almost all the way to that slowly rotating sequence by 600 million years. So this is evidence that there are some of these M dwarfs that make that transition, they jump that gap at very young ages. You also see, if you look at the more intermediate age stars, that they are kind of grouped together on this plot. So if you compare with what's going on at Praesepe, so that's these points here at 600 million years, there's been a slow spinning down of M dwarfs within the rapidly rotating reservoir over the course of a couple billion years. So spin down is happening, but they haven't jumped that gap yet and made that rapid transition. And then the older ones, the ones that are older than 5 gigayears, are both sampling that upper slowly rotating population. So this is all a very handy picture and showcases what binaries can do and tell us about this hard to study M dwarf population. But you'll probably have noticed that there's this point down there. So it's older than 5 billion years, and it's really rapidly rotating and not really consistent with what I've said so far. And so this one is an example of how binaries get in our way. So when we followed up the star, what we found was that it's not just a M dwarf and its widely separated old white dwarf companion, but actually the M dwarf is itself a binary, and a very close binary. So these are the radial velocities that we measured. It's a huge RV signal, and it's basically 2 equal mass M dwarfs that are orbiting each other with a 0.655 day period, so less than a day. And it's not just that these ones are double line binary, that we see it in the RVs, we actually also see it in photometry. It's an eclipsing binary. So this is the data we get from TESS, and that modulation that you're seeing is star spots on the stars rotating in and out of the field of view. And when you phase it to that star spot modulation, you see the trend, but you also see these little V-shaped dips. It's very small grazing transits of the eclipsing binary. And notably, it's at that same period as the rotation period. So it's the spin-orbit coupled system. So the reason why these two M-dwarfs remain active and rapidly rotating out to billions and billions of years is because they're in this spin-orbit coupled configuration. Those interactions between the binary are keeping them active and keeping them rapidly rotating. But when we just saw that on the plot of rotation period versus mass, we didn't know that, so we would have inferred the wrong properties. And I'll also note, because it's an eclipsing binary, we can get the mass and the radii of the components, which we did in this paper that came out last week, if you're interested in more details. And the properties are fully consistent with other similar eclipsing binary systems. So they're fully convective M-dwarfs around 0.32 solar masses. So the next thing that we're looking at to study how these low-mass M-dwarfs are spinning down is a new study where we're looking at wide binaries of both components being M-dwarfs. And what we want to probe is how the spin-down epoch is mass-dependent, because it does seem like the more massive M-dwarfs always spin down first. So we want to test that by identifying systems where one component is active and the other is inactive. And so spin-down may be ongoing. So this is a sample that we're collecting, and we're identifying them using their H-alpha emission, which is a proxy for their rotation rate and their activity. And we've already identified some very interesting systems in this set, but one in particular that I wanted to showcase is this one here. So this is the H-alpha feature that we observe for one star. It's very H-alpha active, and then in its companion, it's not very H-alpha active. And what we need to do is follow this up with higher resolution spectra to make sure that that case I was talking about doesn't happen, that this active star isn't just active because it has a hidden close binary companion that we didn't know about. And so when we went to do that, we found that, no, it's all good. This orange spectrum is a single star. But interestingly, the inactive one was a close binary. And it's a very intriguing system because the most massive star is the most active. And then this close binary pair, once we have those high-resolution spectra, we can resolve the H-alpha of the two stars individually. We find one is only modestly active, and the other is inactive. So it's basically the opposite that we expected to see in terms of the correlation between stellar mass and activity. So it could be that this is suggesting that that picture isn't entirely right, or it could mean that the close binary itself is leading to an early spin down. So it's not just that the existence of a close binary can keep an old star active to advanced ages. It might have a more complex impact on the global picture. So in summary, wide binaries can inform our understanding of M-dwarf spin down, and we can use them to build up this picture of understanding how these low-mass stars slowly spin down within the rapidly rotating mode, abruptly transition to the slowly rotating mode with a significant dispersion in this epoch. But also, we really need to be careful to understand which of the stars we're dealing with are unresolved binaries, because they can remain active to advanced ages and potentially have an even more complicated impact on the overall population. Thank you for your attention. Happy to take questions.
This was very interesting, but since we're talking about stars at the lowest masses, the question is, okay, well, if they have a stellar companion, in principle, you can find it, but what about like either brown dwarfs or planets, like some Jupiter close to them, could it affect their spin down?
Yes, and looking for giant planets around these stars is also another thing that I work on. But I don't know, fortunately or unfortunately, depending on what you're interested in, the occurrence rate of giant planets is very low around these stars, so it's not impacting the population significantly, although it would be very cool when it's there.
Yeah, great talk, Emily. I was wondering, so do you know for all these other systems with high spin downs, if you already know that there are binaries or can exclude that there are binaries, or do you have to like do more follow-up?
For which ones you're talking about? This one?
Yeah.
This? Yeah, so with these, we're getting medium resolution spectra of all these stars. That's how we got the H-alpha, so R of 3000. And then for all the ones that are candidate systems where one is active and one is inactive, we're following them with a trace, so on the 44,000 resolution spectrograph to search for binarity.
very interesting stuff. But I have a theorist question.
Sure.
Is there an accepted explanation for why these guys wait for 2 billion years and then suddenly slow down?
Sure. So the theoretical picture for this is not decided. There's lots of debate. For more massive stars, people like to talk about like coupling between the envelope and the core, but for these fully convective stars, that's not obviously the case. I don't know if Cecilia is here. I'm fond of her model, which is that it's driven by the magnetic morphology of the stars, so that as the star spins down, the morphology of the magnetic field changes, and then that naturally leads to an abrupt transition. So this is the different initial rotation rates coming out of the post-dislocking phase, and then how over time the period would evolve, the rotation period. And you see that this rapid transition comes out of that model. So it might be something to do with the magnetic field.
So it takes 2 billion years to rearrange its field into this spin-down configuration?
Essentially,
and then bang, it slows down.
I think in that picture, the magnetic field complexity is correlated with the current rotation rate. So the initial rotation rate of the star is important, coming out of that post-dislocking phase. So there's a big dispersion of initial rotation periods. And then once it gets to a critical value of the rotation rate, that's when you get that rapid transition. But there's not an accepted answer, so that might not be the answer, but it's one possibility.
Go ahead. So in the plot where you're showing the measured periods for the binaries with sunlight companions, what sets the number of systems where you're able to do these measurements? Yes.
Yeah, so this is from a paper that we put out last year, so you can take a look at that if you want all the details. But so there's 4 white dwarf cooling stars that we use. Those are the triangles. And so that's limited by stars that are, we have rotation periods for the M dwarf mainly. So that we do have more M dwarf, white dwarf pairs where we don't have a rotation period for the M dwarf, but then we can't put them on this plot. And then the diamonds are from sun-like star pairs. So we age the primaries using gyrochronology and also lithium abundance aging. So to do these, we have high resolution spectra of the M dwarf and of the primary, and also rotation periods of the M dwarf. So you need some different things, but you could in theory expand the sample significantly more, especially with dedicated follow-up to get more the rotation periods, which is something that we're working on.
We need to move on. Let's thank Emily.
Okay, so hi everyone. Thank you for the invitation. I'm Christos. I'm a postdoc at MIT, and today I will be talking to you about a paper that was accepted earlier this year, and it's about a very nearby TD. As I will say later, it's probably the closest one detected so far. But before going there, let's talk a bit about what a TD is, or tidal disruption event. So as all of you probably know, most massive galaxies have a supermassive black hole in the center. Now, if there is some active accretion, this then leads to a typical AGN, active galactic nucleus, but most of the time it's a dormant black hole, nothing interesting happens around it. But once every couple thousand years, 10,000 years, 100,000 years, a star might pass very close to the black hole, and depending on the distance, the tidal forces of the black hole might overcome the self-gravity of the star itself, which will happen somewhere here, and then once this happens, the star is completely disrupted, you get this stellar debris, and approximately half of it will come back to the black hole. It will be accreted via a temporally formed accretion disk, and you can even go on and estimate the rate at which this accretion happens, or actually this is the fallback rate from the debris back to the black hole, the vicinity of the black hole, and you can even predict theoretically there's a specific power law that this rate is going to follow, and to first approximation, this is also going to be the flash of the emission that you expect to see. So if you're curious why TDs are important, there are a couple of reasons. One of them is they allow us to study dormant black holes, so it's a unique window into observing black holes in general. Like 90% of the supermassive black holes in the universe are dormant, so this is probably the only good way we can study them. And in addition, because we know very well the boundary conditions, the initial and the final state of the system, we can study the physics of accretion, and maybe we can hope that we understand something that we can extrapolate to other accreting systems. And as you can see, actually, these papers came out in late 80s. This was almost 10 years before we observed any TD. So it was firstly initiated as a theoretical study. And nowadays, we have detected more or less around 100 TDs. You can see the numbers over the years on this plot. We initially found some in the X-rays with old missions like Rosat, but the real revolution came around with the advent of wide field surveys, so optical surveys, ground-based instruments, which you can see here as these green bars. It is interesting to note in this plot there is no infrared detections, and this was from a paper 2 years ago. I think by the end of my talk I will try to convince you this is going to change drastically in the following years. But so we have all these TDs. Now, if you're curious how the actual data look and not just the theoretical predictions, these are some light curves of optical TDs. Is the 1.5-year sample of ZTF TDs, I think. So you can see initially you have a rise time of around 10, 20 days. You reach a peak for a few days, and then you have a gradual decline into quiescence again. And this roughly, most of the times, follow this t to the -5/3 power law decay. So, okay, we have observed all these TDs. It's a very young field for astrophysics standard, and there are still a lot of open questions. I could give a 1-hour talk about the open questions of TDs, but today I will just, for the purpose of my talk, we'll focus on 2 main tensions. The first one is that if you estimate the theoretically expected rate of TDs and you compare it to what you observe in surveys, you find that actually we expect more than we observe at the time. Of course, this is not a very important tension because there are a lot of assumptions. The difference is of the order of few, like 2 or 5. So there are many ways that you can go around it. But the most important tension is that most of TDs have been found to occur in post-Starbird galaxies. And just to give you a better idea of that, we can at the beginning focus on this left plot. So this is a UR color versus stellar mass of the galaxy plot. And what the UR color means is how blue or red your galaxy is. You can see that density contours in the background is the SDSS sample of local galaxies. So you have 2 big areas of galaxies, these blue galaxies down there and the red quiescent galaxies up there. And what you see overplotted as colored squares is where the host galaxies of TDs from the ZTF sample I showed you before lie on this plot. And you can see that most of them, in contrast to what local galaxies do, lie within these 2 green lines, which are the boundary of the Green Valley galaxies. So for some reason, it seems that optically detected TDs prefer to be in a less common galaxy type. The same stands for X-ray detected TDs. So this was a very big issue because if that's true, it tells us something about the galaxy dynamics. There is some preference to have TDs occurring only in post-Starbird galaxies, and a lot of people came up with a lot of enthusiastic ideas how to explain it. But of course, it can also be just a selection bias because this comes from observational data. So the idea that Roth and collaborators put forth a couple of years ago is that this might be well explained by observational biases, and the reason that we don't have a lot of TDs in star-forming galaxies is because there we have much more dust obscuration. So because of surrounding medium, we're not going to observe the TD neither in optical nor in X-rays. So starting from that was kind of our motivating idea, and we want to test whether we can actually detect TDs that are obscured. And if any kind of source is obscured, you have 2 main ways to detect it. Either you go to hard X-rays, which is not very smart for TDs because they're not bright in hard X-rays, or you go to the infrared. So surprisingly, that's what we did. So we went back and used the WISE data archive in order to try to find transits that look like TDs. So for people who are not familiar, WISE is an infrared satellite. It was launched in 2009 and has been scanning the whole sky every 6 months. And by now, it only has 2 operational filters, W1 and W2, which are standard around 3.5 and 4.6 microns. So we went back, we took the whole archive, and we tried to look for transients. And if in the interest of time, I cannot talk too much about that. But if you have questions about how we did it, I'm happy to take questions. And actually, it would be better to just go and talk to Kishele because he's the one who did all of that. And I'm just, I'm using his work, and I also need to skip that for time. But so here today, I'm just going to show you one example of the many transients we found, and we actually found a lot of TD candidates as well. But this is the best example we had, and this is the paper we put out. So what you see here is the flux of any transient over time. So when you see these open squares, is the upper limit. So when you subtract one image from the other, you don't find a transient. The filled squares is the actual detection. So we have this source that, around 2014 is detected for the first time. It reaches 2015 a peak value and then starts going down slowly. And surprisingly, it follows the expected t to the minus 5/3 power law for TDs. It also happened in the center of a galaxy. So the first question you have to answer is, without knowing anything else, is that a TD or not? And without knowing anything else, you cannot answer that. So you have to go and do some more analysis. And we did that. We tried to exclude every other option. So you can imagine this could be an AGN flares all the time. We show that this is not supported by the optical spectrum. It's not an AGN. But then it could be a supernova or a superluminous supernova. It's also transient events that are very common in the universe. But on different arguments, we were also able to exclude this. So by excluding everything else that we could come up with, we just concluded that if it's nothing else, it has to be a TD. And then interestingly, if it is a TD, this took place in a galaxy 42.3 megaparsec away. So this is the closest TD that we know since the beginning of wide field surveys. So it was very surprising to us that just by doing a blind search in infrared data, we could find the closest TD today. And what's even more surprising is that this TD was not detected in the optical. So here are assassin data and pan-star data, and you see that there is no indication of any flaring in this optical data. So this has quite a bit of implications. First, if we detect the closest TD, and this has not been detected in the optical, just by statistical arguments, there is a very large fraction of TDs that we have missed in the optical and X-ray surveys. And just to add, this was also not detected in X-rays. It should have been if it was bright enough. Second, if it's not detected in the optical, it's not detected in the X-rays, it's detected in the mid-infrared, but we argue that it's a TD, the only way to reasonably physically do that is that you have a central TD that is surrounded by a very dusty medium with high covering fraction. So what happens is you don't really see the TD directly, you see the heating of the dust and what the dust emits afterwards towards us. So we found that then, okay, we went on, we did our homework, we took some spectra, we couldn't find anything because it was 7 years later, so no surprise there. But the most interesting part of the paper is actually this plot. So the TD took place in the center of NGC 7392. And this is a plot that's very similar to what I showed you before. You have the UR color, the stellar mass of the galaxy. You have the SDSS contours in the background. Blue squares is from the GTF sample. These magenta diamonds are from the E Rosita X-ray sample. And you can see that both of them are centered are preferentially along the Green Valley. We found that our source is the starburst galaxy. It's close to where the star-forming galaxies lie. So kind of support the argument that was put forth a couple of years ago that there are a lot of TDs in star-forming galaxies and we just miss them because we look in the wrong waveband and they are obscured. So I will just finish with my summary and want to say, we found the closest TD. This has a lot of implication about the rate of TDs, the nature of TDs. If the closest one is obscured, then a large fraction has to be obscured. And at the same time, this one took place in a star-forming galaxy. So this potentially indicates that if we go out and look in infrared, we might be able to find a lot of TDs that were not detected in the optical and might change the demographics of the host galaxies. So I'm going to stop here because I've had time. Thank you.
Aside from the fact that in a star-forming galaxy you have obscuration and therefore you might miss some of these, when you make new stars, you populate orbits that plunge very close to the black hole, and you would have a burst of TDs as a result, because there is a chance that after a while, these stars on plunging orbits are diluted because they go away, they get destroyed. So it's an interesting question to ask if you get more TDs, taking into account the obscuration, more just because you populate orbits that plunge into the black hole. That would be nice to check.
Yeah, that would be great to check. I wish I had a good answer right now, but for the beginning, I think we need to find a good sample of zero biases observationally, and then we can test which theoretical prediction explains better this sample. But for now, like the whole study was that what we see is just selection effects, so we cannot compare directly to theoretical predictions that, like the ones you mentioned. Once we have a very good bias minimum sample, then we can start playing this game of explaining what exact factor plays a game.
Okay, we have two questions. Go ahead.
So, all about the plot, the U minus R versus LOMAS. This plot isn't conclusive because while almost every post-starburst galaxy would lay in the Green Valley, a very small minority of galaxies which are in Green Valley are post-starburst. So if the galaxy is there in its integrated color, you cannot tell that this is a post-starburst until you actually take a spectrum. But my question is, you said that you didn't see it in X-ray, but did you try to look in hard X-ray? Because hard X-ray should not be obscured, so it should be visible.
Yeah, we had a new star observation, but this also took place in 2022, so 7 years after the peak. So, but also I have to say, even if it was during peak, most of TDs have a power law of slope of 3 or 4. You don't expect to see that easily with current instruments because they're very soft. They're very, very soft.
Go ahead.
Yeah, so I have a question about the first point on this summary slide. So how many did you actually find? And then another question is that are there infrared properties really different from the optically detected TDs other than they are just gas obscured?
So for the first question, we have more than a handful, I can say, but we have a grad student working on that, so I cannot give more details right now. But there is a paper coming out soon. But there are a lot even in the nearby universe. So, but for the second question, what do you mean by infrared properties? I missed that. Sorry.
For the optically detected TDs, I think people did infrared follow-up of those TDs. And
Yes.
compared to those properties, these guys have unique properties, or are they
So
just,
what people did in the infrared, if we talk about photometry, they tried to compare photometry infrared to optical, and they found that if there is any dusty medium around, it has to be very low covering factor, like of the order of 1%. And we here show that that's not the case. Like in our case, it should be above 20% at the very least to explain what we see. So I think this aligns well with the selection bias that optical people or X-ray surveys find these low obscuration events. Then once you go to different wavelengths like infrared, you find highly obscured, so high covering factor events. But this is still work in progress, but this is the first hint that there is something different. It seems to be the environment of the black hole.
Let's thank Christos.
Thank you.
So I'm Matt Holman. I'm a postdoc in my 25th year at the CFA. I'm going to talk about ASSIST, an Ephemeris-Quality test particle integrator I recently developed. You can see the paper on arXiv. The title raises 3 questions. So what is a test particle integrator? I'm talking about a special case of the n-body problem where a massless particle is moving in the gravitational field of, in this case, the planets, large asteroids, moon, sun, and other accelerations in our specific solar system. what makes one ephemeris-quality, meaning you can put in a specific time and make a specific prediction of where this thing would be, either in an inertial frame or somewhere on the sky. And why call it assist? I'll get to that later. So let me just get a show of hands. How many people know what JPL Horizons is and you've ever used it? Okay, so Horizons is a web platform where you can put in some object in the solar system, and some observatory, and some time, and it'll tell you where that, what the observations would be. There is, extremely well-developed code behind it that is not publicly available. It can't be easily modified by the users, and it's really not suitable for things like orbit fitting because it's a web interface. There are a number of open source software packages that have been developed for this kind of thing. And so the question is, why would we do this again? To upgrade the language, so you can argue whether C99 is an upgrade from Fortran or whether it's actually a modern language, but also to provide, well, it is fast, okay, I'll say that. So provide a Python interface and move away from file-based processing. And the goal here is really to be ready to have a tool that we can use for data from Gaia LSST, continuing to process DECAM data. So what this is really is, a number of steps. We have to, write down the equations of motion for a test particle in our solar system and really include all the sort of nitty-gritty terms that are included in JPL Horizons, because our goal is to write, sort of make an open source version of this standard of reference. And so we've included this, all the sort of massive objects using the latest. So when you say DE440 or something like that, that's development ephemeris. This is something from JPL. It's basically tabulated form functions that'll tell you how to look all of these things up. And so we have particles moving in that field. We've included actually 3 different forms of GR, a bunch of gravitational harmonics, various forms of representing non-gravitational effects. And on top of all of that, so we've implemented what are called the variational equations. So the partial derivative of each of these equations with respect to the input parameters. So you can use that for orbit fitting. And we built this on top of, or as an extension to Rebound. Rebound is something that many people have probably used. It's a suite of n-body code or various codes, integrators. And we have taken the sort of the workhorse integrator, the IS-15 Gauss-Rado algorithm. And so there's a separate Rebound X way of package for extending Rebound to various things, but we've written our own separate extension because really, unlike a sort of a general purpose thing, this has a specified time scale, masses, the frame of reference, and also, by just making a simple extension to Rebound, we reduce our dependencies to just one other package. So the tests are sort of numerous. The big one is, okay, JPL has this code. They can't share this code with anyone, but what they can do is tell you what the code produces term by term for a specific object at a specific time. So we did that, and then I went through painstakingly making sure that for each of these terms, for each component at that time, we get the same answer to the last digit. And so that's as good as we can do to, demonstrating that at least the equations of motion are correct. And then it's a matter of applying those equations of motion and seeing that in integrations, you get the same, the right answer. And so we've carried out a number of tests, including integrations of me, and Apophis, and this interesting encounter with asteroid 5303 and Ceres. And the speed is actually somewhat faster than JPL's code at this point. So there's one example of a test, and this is what I would call an out and back test. So with test particle integrations, it's a little bit tricky to test them because you don't have conserved quantities. This is a time-dependent Hamiltonian. But what you can do is take a test particle, integrate it out a certain amount of time, turn around, integrate back, and you should get your initial conditions. So this is the difference between the initial conditions and the result as a function of the amount you've integrated out. And the red dashed line there is basically showing what you expect for optimal performance. So if your equations of motion don't have any particular bias, we are all biased, but your code doesn't have to be biased. So this is basically showing that that's optimal performance. Another example is Apophis. Apophis is an asteroid that makes repeated close encounters to the Earth. There's one coming up in April of 29 when Apophis was discovered. This was thought to be one of the big ones that was going to hit us. This is no longer the case. Basically, you just keep observing until you prove that it's not going to hit us. But or you find somewhere to hide. Anyway, this is basically it really does make a significant deflection as it goes near the Earth. So this is actually a stress test because the thing comes it's basically comes a number of Earth radii out, makes this strong deflection. So if you can get this right, you're doing pretty well. This is showing how the step size develops as a function of time. You can see it just plummets down as it goes through the encounter. This is showing the divergence. If I take on the right, take small initial conditions and displace them, they basically track each other out 100 days. They're only different by about a meter, and if you start 10 to the minus 15. So that's a really another strong test. Another is just to basically compare straight up the output between what JPL gets and what we get. And they agree remarkably well. I mean, they basically agree at the limits, until you can't do any better than this given double precision until you go through the encounter. But even after the encounter, the separations is not that great. This is a fun one. So this is the encounter of asteroid 5303 with Ceres, and this in the left panel you're seeing in a frame centered on Ceres, not rotating but just tracking Ceres. You see the asteroid come and make a sort of hiccup past Ceres and continue on. Again, we basically agree as well as possible with what JPL produces. And a graduate student, Zach Murray over there, is one of his projects is to measure asteroid masses from this kind of deflection. And so my hope is that he will actually use this code. Anyway, this is an open source package. You can find it on GitHub. You can pip install it if you wish, if you know what that is. If you don't know what that is, ask a graduate student. Anyway, so future work, is to do not just test particles, but the full n-body problem. I don't think I answered the question about assist. So rebound isn't an acronym. It's about basketball, right? And I have a son who plays basketball. He's really good at assists, so I call it assist. Anyway, I'm now working on the full n-body code, something that basically what JPL uses for the full n-body system. It'll probably be called full court. Anyway, various other upgrades, also doing some work for artificial satellites. This will get used extensively by the Rubin team, and we're working on a few sub-projects. So thank you very much.
Two quick comments. One, there was a term that you didn't include, which at the extremely impressive precision you were talking about 10 minus 14 level.
Yeah.
And that is the fact that the sun changes its mass at the level of 10 minus 14 per year.
Yeah.
And so that you might want to add.
Yeah, I mean, that's true. So Hanno Rhein is one of my main collaborators. He brought that up just a couple of weeks ago, yeah.
And the second question is, sometimes, as you well know from your PhD years, there is chaos. So that means a tiny imprecision blows up.
Yeah.
Do you have any regions of chaos in your solution, like for the objects you were discussing, or nothing?
I mean, it's there, and we certainly have the means because we have the variational equations. We can really test that sensitivity. Clearly the encounters of Apophis with the Earth, since they're repeated, that's chaotic. Every one of those is an exponential stretch. Basically.
So we don't know if it will hit us, do we?
Well, it depends upon your time scale. We know it's not going to get us in the next 100 years. After that, all bets are off.
Okay, so I guess you tailor this time so that you will not be around.
Yeah, exactly. That's the kind of control I have.
Okay, other questions? Let's start with this.
Is there an intuitive way to understand why the optimal scaling in the out and back test goes as like either the off and not flat?
Yeah, well, I'll do my best here. So, in a Keplerian orbit, if you change the period, or it changes the semi-major axis, you're going to change the period not linearly, right? Period squared goes as semi-major axis cubed. So when you're making a numerical error, you're going to change, say, the position or the velocity. You're going to make an error there. That's going to propagate into a change in the energy, which is the semi-major axis, which is going to change the period. So basically, and it's not symmetric. If you make an inward, or you make the semi-major axis a little smaller, you get a 3/2 relationship down or the other way. So basically, it's the nonlinearity in those errors. So even if your errors are unbiased, you can't do better than t to the 3/2.
Yeah, well, first of all, C99 is definitely an improvement over Fortran because people will die.
Yeah.
My question is, actually, did you ever try to offload these computations to a GPU? Because
Yeah, I have not done that, but there are groups. I mean, it is possible to do this. Assist is thread safe, so in principle it could be done where we could talk offline about how, but that's a very good idea.